Are you muted, Professor? I think you might be muted, Professor.
It shows you're still muted.
There should be an icon at the lower left-hand corner of your screen if you're in full view mode. Jump in,
How
anybody.
we doing? How we doing?
There you go. There you go.
Now, who was that just helped me? Who was that?
Nathan.
Nathan. Nathan, humongous thank you for it.
I'll take it. Thank you.
I appreciate that. Nathan, did you turn in your test?
Yes, I sent it in, and I think an email attachment because I didn't see an upload link.
Okay. Everybody else did. I'll take care of that. It'll be all right. But I don't have yours graded yet. But let me tell you how the rest of you did. These are how the grades went on that test. Nathan, I wonder how come you had trouble with that?
I don't know. I think I'd have to look at the email. I think I sent it on maybe Friday or Saturday, so I don't know.
It was in a different place than what it is typically. The same link that you get the exams from, that's where it's just above it. There's a hyperlink and you click it, Nathan, but it was kind of difficult to find.
Huh. I'll tell my IT person about that. It was difficult to send it in, but everybody figured it out. Well, this is how you guys did. We had some A's and some B's, some D's. Do not get discouraged. And today's the 17th of November. And according to this, you do have some homework. It's homework number 24, and it's chapter 9, number 17. One of my excellent students told me that there was a Rankin problem on the test, and I don't think we ever studied the Rankin problem. And I'm amazed at the way you guys, most of you did all right. Because you must have read your book. You must have read your book. Wow, that shows initiative and resourcefulness. We did do a Carnot cycle where you fill in all the blanks, so that was helpful. And I did give you the either the TS or the PV. I think I gave you a TS diagram. between that and reading the book, you guys figured it out. So you're a pretty resourceful bunch. But we do need to study the Rankine cycle and know how to do them. And I was going to do one that's pretty hard. It's harder than the one that was on your test. And it's the one, let's see here. Yeah, this is it. Did I post any Rankine cycle on your content? Does anybody know if I did? I meant to, but I don't know if I did or not. Look on the content. See if I posted a Rankine cycle. It would have been 913. But I wanted to do one that was English. But now where did I put it? Just a minute, let me find it. Sorry, I'm not organized this morning.
I do see any.
It's not on
anything
there.
posted. Oh, sir.
Okay, I didn't get around to it, did I? Shame on me.
Yeah, I can't find it either.
Okay, thank you for looking. Thank you for looking. And I want to do a Rankine cycle. Well, it'd be chapter 9 is what it'd be. All right, just a minute. I'm getting organized here. We're in chapter 9. Let me tell you about the Rankine cycle a little bit, and then I'll find that, and then we'll do it. But that's how you guys did on your test. This is in your book. It's on page 258. And it's called the Rankine cycle. Now, the reason why it's important is the Rankine cycle is how electricity is generated all over the world, and certainly in the United States. Electricity is generated by a form of the Rankine cycle. There are different forms of it, but the basic Rankine cycle has 4 processes. And what we're going to study is the ideal Rankine cycle. And all of these processes are reversible. Perfect. There's 2 adiabats and 2 isobars. 2 adiabats and 2 isobars, and they're all reversible. So that tells us that the reversible adiabats are isentropes. So you could say you have 2 isentropes, if you like. And you remember what isentropes are. Those are when your change in entropy is 0. And they have several pages here describing the Rankine cycles, but the simplest one goes like this. And I would like to find the one that I want to show you. I've misplaced it. Just a minute. Let me dig around. See if I can find it. Yeah, I think this is the one I want here. This is 965. I thought we could do 965 together. Okay. Now that you know what a Rankine cycle is, let's draw the TS diagram and have at it. Let me find it here in the book. We're going to do 965 if I can find it. I wanted to do a no. No, that's not a Rankine cycle. I wanted to do an English problem. And I had a compressor at 1,000 kilopascals. See if we can find it.
You're looking for the question with 1,000 kilopascals?
I thought I was.
Would that still be in the, would that be in the English section though?
Yeah, it should be. No, it wouldn't be, because kilopascals, that's English. That's not English, is it?
Right, that would be the SI or metric or whatever.
Yeah. We know that, doggone it. Okay. All right, well, I'm sorry to waste your valuable time, but I wanted to do an English Rankine cycle. And here's one here. But I wanted to do one where I had the answer book for it. That would be nice to be able to share with you the answers.
On the electronic version of the book, there is one of the questions that has a check answer next to it.
Oh yeah, really? Which one is it?
That's just one that has like a check answer button underneath it if you have the online version.
Oh yeah. Well, I better stick with one that I know for sure. Forget the English problem. We're going to do the one I was going to post for you. And I still can, but I didn't post it. And what this is a Rankine cycle, an ideal Rankine cycle. And we're going to plot up the TS diagram. This is 913. And what it says is steam power plant should produce 10 megawatts of net work. The steam flows at 5 megapascals, 500 C, to the turbine. Okay, you're out here someplace. 500 C. Well, I think that's above the it's above the vapor dome, isn't it? Vapor dome goes up to 374, so 500 C is up here someplace, and a pressure of 5 megapascals. That's 5,000 kilopascals. And here's the turbine. The turbine is at 5,000 kilopascals and a temperature of, I'm trying to do 513. Yeah, 5,000 kilopascals, 500 C. Let's put the 500 C right here. There's the 500 degrees Celsius. And then what happens to it? Well, let's read it. Condenser pressure at 50 degrees Celsius. So down here someplace is 50 degrees Celsius. I think maybe I'm going to change this. Not quite so steep. And this is, I need 50 degrees Celsius. That's your turbine. Okay, keep reading. We're doing 913. Find the mass flow rate of the steam needed. They want us to find the mass flow rate. Well, now, here's our process. There's an isobar. There's state one. That's an isobar right there. Okay, now just a minute now. Of course, that's an isotherm too, isn't it? Go back in your chapter, and you'll see a cycle like this. Here's the pump. Here's state two. Now the pump is an adiabat. It's an adiabat. It's an isentrope. And then there's a isobar that goes from here to here, all the way up there. There's your 5,000 kilopascals isobar. And then here's your turbine. And this is state three. This is state four. This is the condenser. And so you have an isobar here, and you have an isobar here. You have two isobars, and you have two isentropes. The turbine is also an isentrope. This is an ideal turbine. The real turbines won't run like that. They'll be giving you some irreversibilities. But there's your cycle, and now we're gonna do this table of a property table. We're gonna have our temperature, pressure. Let's do it this way. Pressure, specific volume, temperature, specific enthalpy, specific entropy, heat transfer, and work per mass. So we're gonna plot this baby up. Here we go. Now let's see what we know and what we don't know, and we'll fill in our table. Well, we know that the condenser is 50 degrees Celsius. Here's one thing we do know. This is sort of an anchor point that you can count on the ideal Rankine cycle. That's saturated liquid. And we know it's at 50 degrees. So at state 1, we know the temperature is 50 degrees Celsius. And we can look up the pressure. Go to your back of your tables and look up 50 degrees Celsius. No, we don't. Yeah, I wanted to do Fahrenheit and I got mixed up, and I'm sorry, but we are doing Celsius. Go to the back and look up 50 degrees Celsius for me. And what does it say? It says the pressure is 12.350. Can you find that? 12.350. And the specific volume is 0.001012, I think is what it says. Specific enthalpy, see, it's easy to read all this stuff off. The specific enthalpy is 209.31. These are kilojoules per kilogram. Specific entropy at 50 degrees Celsius is 0.7037. Now going from 1 to 2, that's the pump. See, this is the boiler here. But going from 1 to 2 is an isentrope, so that's an adiabat. See, the turbine and the pump are adiabat. So there is no heat transfer going from state 1 to state 2 or from 3 to 4. They're adiabatic. And there's no work. Boilers don't do any work. So going from 2 to 3, there's no work. The boilers don't do any work. They just boil. And the condenser doesn't do any work either, from 4 to 1. So we did great. We got that first line pretty well logged in there. But now what's going on from 2 to 3? Well, that's an isobar. You see this pressure? Oh, we don't know state 2 yet. Just a minute now. We don't know state 2. We do know it's 5,000 kilopascals. But what do they call it when you're out in here? Let me ask one of my excellent students. We're going to ask my friend Alex, unmute and tell the gang what they call stuff out in here. See, this stuff in here is called saturated mixture. But Alex, what do they call it when it's in here? It's state 2.
Condensed liquid?
Condensed liquid, you got it. It's condensed liquid. So let me ask you, Alex, if you're in condensed liquid, which table should you use in the back?
The condensed liquid table?
The condensed liquid table. Good going, Alex. Help me find it.
B.1.4.
Well, now, wait a minute, Alex. They don't, condensed liquid is on this line here. This is called, it's got a different name. It's called compressed liquid.
Ah,
It's compressed liquid. Condensed liquid is this line here.
okay, so that's the actual line.
Yeah, what we need when you're out in here is compressed liquid. And hey, I found it. Look, 500 kilopascals, compressed liquid table. Can you guys find it? We know the pressure at state 2.
Is it
It's
titled
500.
compressed liquid table, or is it the saturated?
No, it's a compressed liquid table. I tell you what, it's table B.1.4. See if you can find it.
I found it. Thank you.
Yeah, good going. Now, the trouble is we don't know the temperature. Dang, we know the pressure at state 2, but we don't know the temperature. But, we do know something. It's an isentrope, so we know that this is 0.7037, the same specific entropy at 2 as 1. Because, see, the change in specific entropy from 1 to 2 is 0 because it's an isentrope. Okay? Hey, look at here. We've got the little s. We'll go to your table and look up 0.7037. They don't have a 0.7037. Well, here, let me show you what they do have on table B.1.4. They have 0.5722, and they have a 0.8308. And what we want is 0.7037. We can interpolate. That's what we're going to do. Now, to get the specific enthalpy, it's 167.98. And 251.51, 251.51. And to get the specific volume, we don't need the specific internal energy. To get the specific volume, and we want 0.00108 and 0.001017. And let's put the temperature in there while we're at it. The temperature goes from 40 to 60.
Mr.
Okay.
Griffin,
Yeah.
are you looking at the 500 kilopascal table instead of the 5,000 one?
Oh, I'm looking at the 500. Who said that?
That's Braxton.
Braxton Honkin, thank you, point for Braxton. I'm on the wrong table. We want 5,000. Thanks to Braxton. It is 5,000, isn't it? Are we doing that? Is that right? Yeah, 5,000. It's not 500, it's 5,000. Good going, Braxton. Okay, guys. Whew. We're gonna start over. We're starting over. But we want the 5,000. And what we want is 0.7037. Well, we can get it. If you have trouble doing this stuff, welcome to the club. You're not alone. Don't ever get the feeling that you're alone. Okay, now we're going to bracket these and we're going to get our answers. And Braxton, double check me now. Make sure that I'm getting all this stuff right. And see, what we want is 0.7037. Okay. Now we're going to fill that in. I am on the right table. It's B.1.4. And these temperatures are going from, I didn't write down the temperature. They're going from 60 to 80. Okay. Go ahead. I'm going to do that. I want you to do it. And we'll see. We'll see what we come up with. Go for it. I know you can do this. Well, I got this one. And this one I got yesterday. Did anyone get any of those?
Yep.
Uh-huh.
Good, excellent. Well, here, let's put this stuff in here. This is how you do it. It takes time and it's tedious. Now notice when you go from state 1 to state 2, your specific volume doesn't change much, you know it? Look at that. That's not a very big change, folks. 0.001012, 0.001008. But the reason why is it's a liquid. See, we're talking with water. This is H2O we're dealing with here. And when you increase the pressure, that's a heck of an increase. We're going from 12 kilopascals to 5,000 kilopascals. The water just doesn't compress much. Liquids are incompressible. So they don't compress much. Interesting. And the H is 214.99. From 1 to 2. Okay, well, let's see. Let's go. Let's see if we can find. Let's go to this one. Now, this one here. This is compressed. This is compressed liquid. This is saturated mixture. But out here, they call this superheated vapor. So we need to go to the superheated vapor chart. We need to look up at state 3, we know that the pressure is 5,000, not 500. I goofed up before, but we got the right pressure now. And we know the temperature is 500 degrees Celsius. And we want to get all of this other stuff, these other properties. Hey, look, we know the pressure and we know the temperature. How about we go PV equals RT? We can't do that, but I want to ask somebody why we can't do it. Braxton, you helped us before. Braxton, tell the group why. We know the pressure, we know the temperature at state 3. Why can't we go PV equals RT, Braxton?
Because it's not an ideal gas.
That's right. It's not an ideal gas. You can't use that equation on water. What do you use? Well, you use the tables. Go to the tables with me. Now, which table? If you're in the superheated vapor region, I would go to the superheated vapor table. Go back there and find it. Superheated vapor. We want what? 5,000 kilopascals. Okay. And what's the temperature? 500 Celsius. All right. Hey, look, there's all the properties. There's a specific volume. It's 0.06857. That's how you get it. You don't use the ideal gas formula. You look it up in the table. What's the specific enthalpy? I'm getting 376. See if you can find that stuff in the table. And for the specific entropy, I'm getting 6.9758. We're doing great. Now that's kilojoules per kilogram Kelvin. Okay. Now we got to go to state 4. You should be on table, well, for that stuff there, you should be on table B.1.3. That's where I found all that. Any questions so far? Okay, well, let's go to state 4 then. Now, what do we know about process 3 to 4? Well, it's an isentrope. If it's an isentrope, the entropy should be 0. The change in entropy from 3 to 4, if it's an isentrope, should be 0. Okay. Well, there's the specific entropy at 3. So the specific entropy at 4 is 6.9758. All right. Now, I think this enters the vapor dome, but let's find out for sure. Go to the saturated table, which is what I call the vapor dome table, and look up 50 degrees Celsius. And if you look at 50 degrees Celsius, this value right here, they call that little SG. And it is 8.0762. 8.0762. I am on table B.1.1. B.1.1. Well, see, 0.7, now just a minute, I'm getting mixed up here. What is the, oh yeah, here we go, 6.9. 6.9, I don't want this stuff anymore. That's just confusing me. I don't need any of that right now. We know the entropy is 6.9, but this value here is 8 point something, so we are inside the vapor dome. We've got some liquid. It's not all vapor. See inside here, they call this a saturated mixture. You have part liquid and part vapor. It's mostly vapor, but there are some liquid. Now there's a problem with the liquid drops. These droplets are going very, very fast, and
Mr. Griffin,
go ahead.
could you repeat that? What were you checking against it to see if it was inside the vapor dome or not? Which value?
Thank you for asking. See, this value right here is called S little f. And this value right here is called S little g. And we are in between there. See, this S little f at 50 degrees Celsius is, thank you so much for asking, it's 0.7037. And this value here, this S little g, is 8.0762. But see, what we want is 6.9758. Well, that's in between. See, 6.9 is in between 0.7 and 8. So we are inside the vapor dome. Did that answer your question?
Yes, it did. Thank you very much.
Yeah, anytime. Now, here's what I'm telling you. You've got water droplets. They're hitting these little delicate turbine fan blades. There's a whole bunch of these little blades. These water droplets are hitting them. Now, they may not break the blade or crack the blade, but if they keep hitting them, and they're hot, they're very hot, and they're hitting these little delicate blades, and they could, in time, corrode or wear away and cause one of those blades to fail, which means that it's going to be slightly out of balance. If one of those little fins, little blades on the turbine goes bad, you could get it out of balance, and they're going to have to shut that whole turbine down. Now, these turbines are bigger than this bedroom I'm in here. They're about twice the size of this bedroom where I'm at, and probably twice the size of the room you're in. They're humongous. They have bolts on them that fasten down. They're really bigger than that. Okay. And you should see the kind of wrenches they have to use. And it's a chore to take those things apart and replace things. And it's expensive. That's why they have two of them. And in the middle of the night, sometimes they'll switch turbines. Have you ever been at 2 o'clock in the morning and the lights kind of flicker off and they come back on? They switch turbines down at the generating plant. So they got two whole turbines. It takes a while to start the new one up and switch the other one over. But there's a problem here. You don't want too many water droplets. It's better if you can get it over here. And so they have different ways of doing that. One of the ways is they extend this up higher. So if this goes up here hotter, then it'll come down here and it won't enter the vapor dome. And that's good. The way they make it hotter is they have another coil they put in the very hottest part of the flame. See, they're burning coal, okay? But I'll tell you something about, you can get a candle, and you can see this. A candle, go get a candle. It kind of has a blue part in the middle. If you ever look at a candle closely, it's kind of got a blue part here in the middle. And then the, I don't have an orange, but this part here is sort of orange. You know where the hottest part of the candle is? It's right there. It's not up here. That's not the hottest part. The hottest part is right there. They have another tubing, a coil, that the boiler has a coil that's in the very hottest part of your flame, and so they bring this up a little higher, all in an effort to keep from getting too many water droplets. You can take a whole course in this Rankine cycle business. It can be your major. You can do your senior project. You know, you write a paper on it, and they can make them complicated. Here, let me show you a fancied up turbine here in chapter 9. Let's see if I can find it here. Wait a minute. Yeah, here we go. If you look on page I'm trying to find this one where they've tried to increase the efficiency of your turbine. Yeah, there's one. This is on page 271. They have two different turbines. They have a high pressure turbine and a low pressure turbine. On 271, this is a much more complicated power generating system than what we're talking about. We're just doing a simple one, a simple ideal Rankine cycle. Theirs is a Rankine cycle, but it's a little more complicated. So you see, here's the thing, they're burning this coal, and it costs money. We have lots of coal in Oklahoma, but it's got sulfur in it. And so it makes this obnoxious sulfur dioxide or whatever, and other stinky gases. So we buy our coal from Colorado. Have you ever been going to school or someplace, and ding, 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 here comes this train of 110 cars, coal cars, okay? And you count them, swish, swish one, swish, swish two, swish, swish three, and you're late already. Well, I'd hate to have to pay for one of those loads of coal, one of those full coal cars. It costs money. If you could just get 1% more efficient, if you could figure out a way to run this Rankine cycle and have 1% more efficient, you'd probably pay for your time at your company for the rest of your life. Are you with me? That's a lot of money, a lot of coal cars. And that's what some people do. They try to figure out a way to get a little bit more bang for the buck. Well, enough of that BS, I call it, and let's go on and figure out the rest of this. Now, state 4, we think, is in the saturated mixture region, so we're going to have to go to our vapor dome table, and we need 50 degrees Celsius vapor dome table. And here's what we're going to do. We're going to go S4 is equal to SF plus the quality at 4 times FSG. Now we know what the specific entropy is at state 4. It's 6.9758. And you can look this up at 50 Celsius. Here goes, I'm looking it up. I'm getting 0.7037. And now we're going to get our quality at state 4. Double checking now, make sure I'm getting the right number, 7.3725. Okay, go ahead and help me get that quality. And I'll be quiet for a tiny minute. And we're trying to find the quality at state 4. I wonder if I did that right. I'm getting 0.8507. If you got that, say uh-huh.
Uh-huh.
Yeah. Now, you know what that means? That means you're 85% vapor and you're 15% liquid. That's what quality means. It's the amount. Let me move that. Yeah, there we go. We're 15% liquid and 85% vapor. And now, see, we can get these others. Now, the pressure, it's the same as at 1. See, 1 and 4 have the same pressure because they're isobars. Remember, Rankine cycle has 2 isobars. So this is 12.35 kilopascals. Now we're going to get the V and the temperature. Well, we know what that is. It's also an isotherm because inside the vapor dome, condensing is isothermal. But we're going to get the V and the H, and here's how we're going to do it. Make a little rhyme here. We can't use that ideal gas law. I graded some homework that you guys turned in. And it seems like there's 2 ways to go wrong on some of this. One of them is you don't put a vapor dome on there. You're dealing with water and you don't put a vapor dome on there. Well, you're supposed to. If you're dealing with water, it's going to have a vapor dome. And then the other mistake is you have something like helium, which is an ideal gas, and you'll put a vapor dome on it. Well, you don't need a vapor dome with helium. It just stays in the gaseous state the whole time. So vapor dome, no vapor dome. Get it right. Okay, here we go. We're going to get the specific volume at state 4. Go to your tables and help me find these numbers. 0.001012. That's right there. Plus 0.8507, 12.0308. And see, we can get our specific volume. And then for the specific enthalpy, it's going to be 20931 plus our quality times 2382.75. All right, go ahead and get those and we'll fill them in and we'll finish our table and discuss it. Go for it. And I hope somebody's checking me on this. This is what I'm getting. Anybody getting those? If you are, say, uh-huh.
Uh-huh.
Yeah. Well, we're doing great. We just have to fill in these boxes and discuss the rest of the problem. Now, the way you fill these in, these are going to be kilojoules per kilogram. Is you use the first law. If you go to one of these generating plants, there's one down by the river. If you cross the bridge on I-44 going to Oklahoma City at night, look over to your left, you see a bunch of lights down there downstream. That's a power station down there. And the water they use is distilled water. They have a big spherical tank filled with distilled water. See, they don't use the tap water because our tap water's got, I don't know, sodium carbonate or something in it that it'll coat the pipes, and your water heater after a few years doesn't work as good because it's got this buildup in it. So they use distilled water. And that water just goes around and around in this circle. It's liquid here, and then it's compressed liquid, and then it's a saturated mixture, and then it's a superheated vapor, and then it goes through the turbine. It's all vapor, and then it comes down here to state 4, and it's mostly vapor, but with some liquid, and then it condenses. And you're at saturated liquid here, and it goes around and around. Same water goes around and around the whole time. Well, let's figure out these. Let's figure out this work per mass. Here we go. First law. We just need some room. We got all the numbers. We don't need this stuff in here anymore. This is how you get the numbers from the tables. Maybe it's good I couldn't find that English one. The English ones are so tricky with all the pounds and the divide by 778.17 and multiply by 144. It can get confusing. By the way, the next thing we'll tackle is refrigeration cycle. So if you want to read ahead, that's what we'll be doing. Okay, first law. Now you got to use the right first law. I think I gave you a page on content of the different first laws. The one you want is this one here. I don't think we need the kinetic and potential energy terms. You can throw them out. This would be 0 because it's a steady state deal. This turbine just sits there and hums. You check the pressure gauges and they're supposed to stay the same. Unless somebody forgets to put fuel in every once in a while. The temperature should stay the same. And if we're going to do 1 to 2, it's an adiabat. We'll do 1 to 2. If it's an adiabat, well, you don't have any heat transfer. It's an isentrope. And if you divide through everything through by m dot, you can just have your little w from 1 to 2. And here, this will just be h1 minus h2. Okay, well, we got it. Here's h1, here's h2. Go ahead and go ahead and do that for me. And we'll see what the little w is, the work per mass. Did you get the work of the pump is a negative 5.68 kilojoules per kilogram? And if you did, say, oh, okay, good going. We
Wait,
got it. Let's
I'm
put.
confused. On
I'm
the
sorry?
which one's H1 and which one's H2 in this scenario?
These are all initial values. These are initial values. So H1 would be the 20931. And see, here's P1, this is P2, this is P3, this is P4. This is V1, V2, V3, V4, T1, T2, T3, T4, H1, H2, H3, H4. So did you get negative 5.68? I'll show you a way you can check that. Let's see if I need a little room here to show you. Yeah, here's some room right here. We don't need that stuff there. You understand that. Do you remember I showed you on your PV diagram? The pump pretty much looks the same on the PV diagram. It goes straight up. Because liquids are incompressible. But the work done on a control volume like a pump, it's a control volume. See, mass comes into the pump and mass goes out of the pump. And I'll show you what happens. The work done, it's not under the graph, it's under the graph sideways. Let me see if I can show you that in the book. Just a minute now, I gotta shop around to find that. Can you find that for me in the book there where it shows you that? Yeah, here it is. It's on page page 218. If you look with me on page 218, see, you're used to work being underneath the graph. Well, it is for control masses. See, if you have a control mass, it's the work under the graph. The work is under the graph. If you have a process like this with a control mass, but we don't have a control mass. Pumps are not control masses. They have mass going in and mass going out. And can you see on page 218, if you have a control volume, the work is sideways? Well, see, we can figure it. In this case, it's a rectangle. And this value here is 12.35 kilopascals. And this value here is 5,000 kilopascals. And this value here is 0.00001. Well, actually, it changes from 12 to 8. So why don't we just make it 0.001010, kind of in the middle, because there's a teeny tiny slant to it. Okay, so how do you find the area of a rectangle? Well, you take the base. Well, the base is 0.001010 cubic meters. Is this showing up? Barely. Cubic meters per kilogram times the height. Well, that I can't do that in my head. It's 5,000 minus 12.35. 49, call it 88 kilopascals. Now I want you to multiply that with me. Take the 4988 and multiply by 0.001010, and I'm getting 5.04 kilojoules per kilogram. Now, it doesn't give you the minus sign. You just have to know that pumps give you negative work. So we're off a little bit. We got negative 568, and we're getting negative 504 using this method here. We're off a little bit, but we're in the ballpark. So that's another way of getting the work per mass of the pump. My problem was I didn't know what to use really for the for the base of my rectangle. But I'm in the ballpark. Okay, let's go on. Let's get the heat transfer for the boiler. Now this is from 2 to 3, and we're going to use the first law for the boiler. Okay, here goes. We're going to do that. I'll write it above this. Well, this is the boiler is steady state. Everything in here is steady state. But you don't throw out the heat transfer term. That's a keeper. You can divide through by m dot and just get the little q from 2 to 3. Minus 0. There is no power. Boilers do not require power, and they do not provide power. We divided through by m dot. And so from 2 to 3, you're going to have H2 minus H3. Okay, plug it in. Let's see what you get. I'm getting a positive. I'll just round it off. 3219 kilojoules per kilogram. Well, what does a positive heat transfer per mass mean? Does that mean? Let me ask somebody. Let me ask my friend Brian. Brian, unmute and say hello, Brian.
Hello.
Yeah. Hey, Brian, we're getting a positive heat transfer per mass for the boiler. Is that heat transfer going in to our boiler, or is that heat transfer coming out? What do you think?
Okay, I always get this wrong, but I'm gonna say
Positive heat transfer going in or out?
From 2 to 3.
2 to 3.
Yeah, it should be going in.
Yes.
Yes. Okay.
Good going. Excellent. It's going in. See, if you get a positive heat transfer, here, I'll draw it for you. Here it is. This is your heat transfer Q23. It's going in. Now the condenser, there's your heat transfer Q41. That heat transfer is going out. It's going out. You know what they do? They have coolers. They have these big, huge things, and they use the river water to cool it. They try not to heat up the river water too much. See, when you cool off this steam in this plant here, what happens is you use the river water, and it makes the river water warmer, and that's bad for the fish. The fish don't like the warm water, and so they try not to heat it up too much. But you've seen those towers, those cooling towers. If you go to one of these plants, they have cooling towers. And they like to have them by rivers, if you'll notice. Okay, well, we did great. Now let's do, we better speed it up here. Let's find the work per mass for the turbine. Now, this is the whole reason why we have a Rankine cycle, to provide power. See, this is where you get your power, W dot. Turbines provide power. Okay, well, let's write the equation for that. Well, it's the same old thing. Every process we have here is steady state. And so you don't have any change in total energy with respect to time. You do with location. You have a change in properties with location for sure. Well, look at all the properties. They're changing. Look, the pressure changed from 12 to 5,000. That's a big change. But it didn't change with time. The pressure going into the pump is 12 before in the morning, and you eat your lunch, you come back, and it's still 12. See, the pressure doesn't change with time. It just changes with location. So that's 0. We're doing the turbine. It's an adiabat, so that's 0. This is a keeper. Only if you divide through by m dot, you can write little w 3,4. H3 minus H4. We'll throw out the other terms. Find the work per mass of the turbine. Go for it. We're doing the turbine now. Well, I got an answer. I got 3197.5. Did I do that right? Somebody say, uh-huh. Or if I did it wrong, just say, uh-uh. Say, nuh-uh.
Maybe nuh-uh.
Yeah, I'm getting a different answer.
All right, thank you so very much. I must have done something wrong. Let me try again. Thank you very much. How come I still got that? Oh, now wait a minute. Wait a minute, I can't read my own writing. You guys are so sharp. How about this? That's wrong. That was wrong. How about that one?
Uh-huh.
Yeah.
Yeah. Well, let's finish this off. I only got a couple of minutes. Now this one, you do the same doggone thing, only here is where you take H4 and you subtract H1. Let me do that. This is the condenser, and now this is going to be a minus 2027. Now what we're going to do is we're going to add these up, and this will give us our net work per mass, and this will give us our net heat transfer per mass. They should be the same according to the first law. Add these up and let's see if that's true. I'm getting 1192 when you add these up. Let me add these up and see what happens. This rounds off to 1192. That's good. There's your net work. There's your net heat transfer per mass. And the last thing that we're going to figure is the efficiency of our cycle. And then I think that's enough. Read ahead on your refrigeration cycle. Do your homework. But the efficiency is going to be this net work per mass divided by the heat transfer, in this case, from 2 to 3, because you got to pay for that. Somebody has to pay for that coal. So let's see what it is for this one. This is 1192, and this here is 3219. So this one is 37% efficient. So for every $1's worth of coal you buy, you're getting 37 cents worth of power. That's kind of pathetic, isn't it? Okay, do your homework, read about the refrigeration cycle. We're going to get out of here, and I wish you well. I'll see you next time.
Professor?
Bye-bye, students.
Professor, do we have class on Thursday next week?
Oh, that's a good question. Let me see my calendar.
Does anybody else know offhand?
Now, just a minute. This is the.
I don't think we do.
No. There will be no class next Thursday. There is Tuesday, though.
Okay, great. That's what I was looking for. Thank you.
I'll see you Tuesday,
Sounds good.
but no
Quick
class
question.
next Thursday. It's Thanksgiving.
I have a question,
Okay.
Professor.
Bye-bye, everyone.
Wait, there's a
Bye-bye.
question. There's a question.
Yeah.
There's a,
Oh, yeah, go ahead.
Yeah, I have a question. I emailed you, but you didn't reply back to me. I was asking about the grade, like where I standing, because I was a little bit confusing to how to do those maths to
Okay,
figure
well,
out.
let me look up my records, Mohammed, and
That's Reagan.
oh, I'm sorry, Reagan. Yeah, I know your voice. I know you, Reagan. And I can email you back. Let me do that this afternoon. I'll look up your email and I'll respond.
Okay, I appreciate that. Thank you.
I will. Thank you. Anybody else? Okay, ta-ta,
Thank you.
everyone. Thank you.